Close your eyes for a moment. Picture the night sky, a tapestry of infinite light woven from stars, galaxies, and nebulae. We think of the cosmos as something full, teeming with matter and energy. But what if the most important discovery wasn't something we found, but something we didn't? What if there's a place in the universe defined not by what's there, but by an unnerving, impossible absence? Tonight, we journey into such a place, a region of profound emptiness, known as the Eridanus Supervoid. Prepare to drift into the heart of the great nothing, a place that challenges the very foundations of our cosmic model. This is a story of a chilling mystery, a cosmic question mark painted across the sky, and together we will explore the theories of what could possibly be hiding inside the emptiness. To understand the void, we must first understand the echo of creation itself. It's called the cosmic microwave background, or CMB. Think of it as the universe's first photograph. It's the faint, residual heat from the Big Bang, bathing everything in a gentle, almost uniform glow. For decades, cosmologists studied this glow, and it was remarkably consistent, with only tiny, expected temperature fluctuations. It was the perfect baby picture of our universe. But then in 2004, a satellite named WMAP gave us a clearer view and revealed something deeply unsettling. In the direction of the constellation Eridanus, there was a patch of sky that was unnaturally, inexplicably cold. It wasn't a small blip, it was enormous. This was the CMB Cold Spot, an anomaly so statistically improbable it was like finding a patch of ice in the middle of a desert. The foundation was laid for a decade-spanning mystery. Was this cold spot a fluke, or was it pointing to a structure of unimaginable scale and significance? So, what does it mean for a part of the sky to be cold? When we look at the cosmic microwave background, we are seeing light that has traveled for over 13 billion years. This light is incredibly ancient. Its temperature is a direct measure of its energy. The average temperature of the CMB is a frigid 2.73 Kelvin, just a whisper above absolute zero. The fluctuations are minuscule, measured in millionths of a degree. But the cold spot was different. It was significantly colder than the surrounding space, a deviation far beyond what our standard models of the universe predicted. It was a clear, defined patch of less energy. Imagine a perfectly smooth, warm pond. The CMB is like that pond. A few tiny ripples are normal, but the cold spot was like finding a large, deep, cold pothole in the water. It was a signal that something had happened to the light from that direction. Something had sapped its energy on its long journey to us. 2. The initial reaction from the scientific community was skepticism. Could it be an error in the satellite's instruments, a flaw in the data analysis? But as more data came in from WMAP and later from the more powerful Planck satellite, the cold spot remained. It was real, it was there, and it demanded an explanation. This wasn't just another data point, it was a fundamental challenge. It hinted that the universe, on its grandest scales, might be even stranger and more mysterious than we had ever imagined. The search for the source of this chill had officially begun. The first and most logical step in solving this mystery was to point our most powerful telescopes at this specific region of the sky and see what was there, or more accurately, what wasn't. For years, astronomers conducted deep sky surveys, meticulously mapping the distribution of galaxies in the direction of the cold spot. This is painstaking work. It involves charting the positions of thousands, even millions of galaxies, one by one. The goal was to build a three-dimensional map of the cosmos in that particular slice of the sky. And as the map took shape, an astonishing structure began to emerge from the data. It was a void, but not just any void. It was a supervoid, a colossal, almost unbelievable bubble of emptiness. This region was found to be drastically underdense. It contained far fewer galaxies and far less matter than any other surveyed part of the universe. It was a cosmic desert, an abyss of staggering proportions. The Eridanus Supervoid, as it came to be known, was the leading suspect for the cause of the cold spot. The connection seemed almost too perfect, a giant cold spot in the ancient light and a giant hole in the fabric of space perfectly aligned. The question was no longer if there was a void, but how a void could create such a profound chill. Let's try to wrap our minds around the scale of this structure. When we say supervoid, the word doesn't quite do it justice. The Eridanus Supervoid is estimated to be between 500 million and 1 billion light-years in diameter. 1 billion light-years. Our own Milky Way galaxy, with its hundreds of billions of stars, is a mere 100,000 light-years across. You could fit 10,000 Milky Way galaxies end-to-end across this void, and you would still have room to spare. It is one of the largest structures ever discovered by humanity. To travel across it, even at the speed of light, would take 1 billion years. It is a region of space so vast that it represents a significant portion of the observable universe. And when we say it's empty, we don't mean it's a perfect vacuum. There are still galaxies within it, but they are incredibly sparse. The density of matter inside the Eridanus Supervoid is about 30% lower than the cosmic average. Imagine flying through a bustling city with skyscrapers and lights everywhere. That's a normal part of the universe. Now imagine flying into a region where the city just stops. For an impossibly long distance, you see only a handful of distant, lonely streetlights. That is the supervoid. It is the silence between the notes of the cosmic symphony, a pause of unimaginable length and depth. So we have our culprit, a colossal void, and we have our crime scene, a mysterious cold spot. Now we need the mechanism. How does a lack of matter in one place make ancient light colder? The answer lies in one of the most fascinating and counterintuitive battles in the cosmos, the fight between gravity and dark energy. The prevailing theory is something called the integrated Sachs-Wolf effect, or ISW effect. It sounds complex, but the idea is beautifully simple. Imagine light as a tiny marble rolling across a rubber sheet representing space-time. As a marble of light enters a region with a lot of matter, like a galaxy cluster, it rolls downhill into the gravity well. It picks up energy and becomes slightly bluer, or hotter. As it climbs back out of the gravity well, it loses that same amount of energy, returning to its original state. In a static universe, this would be a zero-sum game. But our universe is not static. It's expanding, and that expansion is accelerating, driven by a mysterious force we call dark energy. This is the crucial part. Now imagine our marble of light entering the Eridanus Supervoid. It's not a gravity well, but an anti-well, a shallow hill it has to climb. It loses a tiny bit of energy as it enters. While it's crossing this billion light-year expanse, the universe continues to expand. Dark energy stretches the void, making it larger and shallower. By the time the light is ready to leave the void and roll downhill again to regain its energy, the hill is flatter than it was when it entered. It doesn't get all its energy back. The net result is a tiny loss of energy. The light comes out slightly redder, slightly colder. This is the ISW effect, a cosmic tax levied by dark energy on light crossing the largest voids. The integrated Sachs-Wolf effect is an elegant and compelling explanation. It connects three of the most fundamental components of our universe: the ancient light of the CMB, the large-scale structure of matter, and the accelerating expansion driven by dark energy, it perfectly explains why a supervoid should, in theory, leave a cold imprint on the CMB map. It seems like the case is closed. The void did it. But in cosmology, things are rarely so simple. When scientists did the math, a problem emerged. They calculated the expected temperature drop from a void of this size and emptiness based on our current understanding of dark energy and gravity. And the numbers didn't quite add up. The observed cold spot is much colder than the ISW effect from the Eridanus Supervoid should be able to account for. The void is big, but it's not big enough or not empty enough to explain the entire chill. The Sachs-Wolf effect can explain some of the coldness, perhaps even a significant fraction of it. But there is still a residual coldness that remains unaccounted for. This is where the mystery deepens. The smoking gun isn't a perfect match for the suspect. It's like finding a footprint at a crime scene that is the right shape, but the wrong size. It leaves the door open for two possibilities. Either our understanding of gravity and dark energy is incomplete, or something else is contributing to the coldness, something far stranger. Let's pause and consider the first of those two possibilities. What if the Eridanus Supervoid is not the problem, but our theory is? The lambda CDM model is the name for our standard model of cosmology. It's the framework that describes the universe as being made of normal matter, and dark energy, represented by the Greek letter lambda. This model has been incredibly successful at explaining a vast range of cosmic observations, from the CMB to the distribution of galaxies, but it's not perfect. It has a few nagging issues, and the cold spot is one of them. The discrepancy between the predicted and observed temperature drop could be a sign that lambda CDM is missing something. Perhaps dark energy isn't a constant, as the model assumes. Maybe it evolves over time, or its effects are different in these massive voids. Or perhaps gravity itself behaves differently on such immense scales, a deviation from Einstein's general relativity that we can only detect in extreme environments like this. The Eridanus Supervoid, therefore, acts as a massive cosmic laboratory. By studying this anomaly, we are stress-testing the very pillars of our cosmological understanding. The void is forcing us to ask uncomfortable questions. Is our best model of the universe truly complete? Or is this billion light-year hole in space also a hole in our knowledge, pointing the way toward a new, more comprehensive theory of everything? So if the void alone can't explain the coldness, and we aren't ready to throw out our entire model of cosmology just yet, what other options are there? This is where the theories move from the realm of the merely astronomical to the truly mind-bending. Let's start with the idea of a statistical fluke. In any random dataset, you will eventually find strange patterns just by chance. Think of flipping a coin. Getting 10 heads in a row is unlikely, but not impossible. Could the cold spot be the cosmological equivalent of that? A 1 in 1,000 or even 1 in a million chance alignment? The idea is that the supervoid is real, and it creates a cold spot via the ISW effect. But purely by chance, this region of the CMB was already a bit colder than average to begin with. The two effects, the random cold patch and the void, just happened to line up perfectly, creating one super cold region. It's a tidy explanation. It requires no new physics, no rewriting of the rules. It simply requires us to accept that we live in a universe where incredibly unlikely coincidences can and do happen. Many scientists find this to be the most plausible, if least exciting, explanation. It's the cosmic shrug theory. The universe is vast and old, and given enough time and space, improbable things are bound to become probable. But for others, relying on sheer luck feels unsatisfying. It feels like we're missing the bigger, more profound picture. What if the explanation isn't a coincidence, but a relic from a far more violent and chaotic era. We must travel back in time to the very first moments after the Big Bang. In these fractions of a second, the universe was a maelstrom of energy, undergoing phase transitions similar to water freezing into ice. Some theories of physics predict that as the universe cooled and settled into its current state, defects may have been left behind like cracks in the ice. These are not defects in matter, but defects in the very fabric of space-time itself. One such proposed defect is called a cosmic texture. Imagine a vast, tangled knot of energy left over from the earliest moments of creation. This texture would be a huge, transient structure that would have briefly dominated that region of space. As it collapsed and unraveled in the early universe, it would have sent out a powerful gravitational wave, a ripple in space-time. This ripple expanding outwards would have stretched the light passing through it, sapping its energy. It would create a cold spot on the CMB. In this scenario, the supervoid we see today would be a secondary effect. The immense energy of the collapsing texture would have pushed matter and energy away from the area, effectively blowing a bubble in the cosmos and creating the void we observe. So the void didn't create the cold spot. The same primordial event created them both. Let's push the boundaries of imagination even further. The standard model of cosmology is not the only game in town. There are other, more speculative ideas about the ultimate nature of reality. One of the most intriguing is the multiverse theory, the idea that our universe is not unique but is just one bubble in a vast, churning foam of other universes, each with potentially different laws of physics. If this is true, it's possible that in the distant past our universe collided with another. It wouldn't be a destructive event in the way we might imagine, but more of a gentle bump. Such a collision would have been a cataclysm on a quantum level, leaving a lasting scar on our cosmos. This cosmic bruise would manifest as a disturbance in the energy of space-time. The gravitational pull from the other universe would have subtly warped our own, creating a region with a different energy density. This disturbance would be visible to us today as a large, circular anomaly on the cosmic microwave background, a cold spot. Proponents of this theory point to the almost perfectly circular shape of the cold spot as potential evidence. It looks like a bruise. In this breathtaking scenario, the Eridanus Supervoid is not the cause, but a symptom. The region was disturbed by an interaction with another reality, and the formation of galaxies was suppressed, leading to the creation of the void. If this theory is true, when we look at the cold spot, we are looking at a fossil, the fossil of a gentle touch from a neighboring universe. The multiverse collision hypothesis is, without a doubt, the most extraordinary explanation for the cold spot. It transforms it from a mere astronomical curiosity into potential evidence for a reality far grander than we can perceive. But it's also the most difficult to prove. How could we ever distinguish a cosmic bruise from, say, a cosmic texture or a simple statistical fluke? Scientists are looking for subtle clues in the data. A collision might not be perfectly symmetrical. It could leave behind specific patterns in the polarization of the CMB light, like a faint fingerprint of the interaction. Researchers are reanalyzing the detailed maps from the Planck satellite, searching for these telltale signs. So far, the evidence is inconclusive. Some studies have found tentative hints that support the multiverse model, while others have found nothing at all. It remains a tantalizing but unproven possibility. It's important to approach such ideas with a healthy dose of scientific skepticism, but it's equally important to appreciate the sheer audacity of the question being asked. The fact that we can even formulate such a hypothesis and search for evidence of other universes within the data of our own is a testament to how far we have come. The cold spot forces us to be bold, to consider ideas that live on the very edge of science and philosophy. With so many competing theories, from the mundane to the multiverse, how do we move forward? The answer, as always in science, is with more data. We need to create a better, more detailed map of the Eridanus Supervoid. Current surveys have given us a rough outline, but we need to fill in the details. We need to know its precise shape, its depth, and how the few galaxies within it are distributed. Upcoming projects are poised to do just that. Telescopes like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to map the universe on an unprecedented scale. Euclid, in particular, will create a vast 3D map of the cosmos, charting the positions of billions of galaxies. Its gaze will inevitably pass over the Eridanus Supervoid, giving us the sharpest view yet of its structure. This new data will be crucial. If the void turns out to be larger and emptier than our current fuzzy estimates suggest, then the standard integrated Sachs-Wolf effect might be enough to explain the entire cold spot after all. The mystery would be solved and our standard model of cosmology would be strengthened. It would be a less dramatic conclusion, but a powerful confirmation of our theories. But what if the opposite happens? What if these new, ultra-precise maps confirm our current estimates? What if they show definitively that the supervoid is simply not special enough to create the entire cold spot? That would be a far more exciting result. It would effectively rule out the simplest explanation. The void did it theory would be off the table. This would force the scientific community to take the more exotic alternatives much more seriously. The statistical fluke argument would still be possible, of course, but it would become less palatable as the discrepancy becomes more sharply defined. A confirmed mismatch between the void and the spot would be a powerful piece of evidence that new physics is required. It would ignite a new fire in the search for cosmic textures, multiverse collisions, or other, as yet unimagined, phenomena. In this way, the Eridanus Supervoid is a perfect no-lose scenario for science. Either we confirm and refine our existing model of the universe, or we find compelling evidence that we need to tear it down and build something new. Whatever the answer turns out to be, we are guaranteed to learn something profound about the nature of the cosmos. The emptiness itself is a signpost pointing the way toward a deeper truth. Let's take a moment to debunk a common misconception. When we hear the word void or hole in the universe, our imagination can run wild. It's easy to picture a region of absolute nothingness, a terrifying black abyss where the laws of physics break down. This is not what the Eridanus Supervoid is. It is not a hole in space-time. It is not a portal to another dimension, at least not in any way we can interact with. It is simply a region of space that is underdense in matter. If you were to travel there in a spaceship, you wouldn't notice anything particularly dramatic. You would still be in the vacuum of space, surrounded by the same physical laws that govern us here on Earth. The only difference would be the view. The sky would be much, much darker. The brilliant river of the Milky Way would be gone. The sky would be punctuated by only a few, incredibly distant and lonely-looking galaxies. It would be a place of profound solitude. The emptiness is a relative term measured on a cosmic scale. The supervoid is empty compared to the rest of the universe, but it is still filled with the same dark matter, dark energy, and faint glow of the CMB as everywhere else. It is not a place of nothing, but a place of less. And it is in this less that the profound mystery lies. The existence of structures like the Eridanus Supervoid has a profound philosophical implication. It reminds us of our place in the cosmic web. Our planet, our star, and our entire Milky Way galaxy exist within a filament of matter. We live in one of the bright, bustling cosmic cities, and this is not a coincidence. Life, as we know it, requires heavy elements, which are forged in stars. Stars are born in dense clouds of gas, and these clouds are found within galaxies, which in turn are found within the filaments of the cosmic web. We are, by necessity, creatures of the densest parts of the universe. The voids, by their very nature, are likely to be truly sterile. With so few galaxies, there are far fewer stars, fewer planets, and fewer opportunities for life to arise. When we look towards Eridanus, we are looking at a region of the universe that is fundamentally inhospitable to the kind of complexity that led to us. It is a stark reminder that our existence is tied to our specific location. We are not just in the universe, we are a part of its structure, a product of its densest and most vibrant regions. The Great Nothing provides the contrast that allows us to appreciate the richness of our cosmic home. The story of the cold spot and the supervoid is a perfect illustration of how science works. It begins with an unexpected observation, an anomaly that doesn't fit the current theory. This is followed by skepticism and rigorous attempts to check the data. Once the anomaly is confirmed to be real, the search for explanations begins. Multiple hypotheses are proposed, ranging from simple extensions of existing theories to wild speculative new ideas. Each hypothesis then makes predictions that can be tested with further observations. This is the stage we are in now. We are building the tools, like the Euclid telescope, that will allow us to test these predictions and begin to rule out some of the possibilities. It is a slow, methodical process, driven by curiosity and a relentless pursuit of evidence. There is no single eureka moment, but rather a gradual accumulation of knowledge that slowly chips away at the mystery. The answer might not come tomorrow or even in the next decade, but each new piece of data, each new analysis, brings us a little bit closer to understanding what truly lies at the heart of this cosmic emptiness. Let's return to the human element of this story. Imagine being one of the scientists who first saw that WMAP data. You are looking at the most detailed picture of the infant universe ever created, the result of years of work by hundreds of people. You expect to see a beautiful, almost uniform map confirming your models, but instead your eyes are drawn to this giant, cold bruise, a feature that simply shouldn't be there. Think of the mix of excitement and unease, the thrill of discovering something entirely new, something that could change everything, but also the daunting realization that the universe might not be as well behaved or as well understood as you thought. It's a moment that redefines the boundaries of the known. This is the emotional core of scientific discovery. It's not just about numbers and equations, it's about confronting the unknown. It's about the courage to say, I don't know what this is, but I'm going to find out. The cold spot is more than just a temperature anomaly. It's a symbol of cosmic humility. It's the universe gently reminding us that no matter how much we learn, there will always be new mysteries waiting for us just over the horizon, hidden in the light, or in this case, in the cold. Beyond the specific physics, the Eridanus Supervoid taps into a very deep and primal aspect of the human psyche, our relationship with emptiness. Throughout history, we have often viewed voids and vacuums with fear or suspicion. Nature, it was said, abhors a vacuum. We fill silence with noise and empty spaces with things. Yet in many philosophical and spiritual traditions, emptiness is also seen as a source of potential, a blank canvas upon which anything can be painted, a moment of silence in which true understanding can arise. The supervoid is the cosmological embodiment of this dualism. It is a place of less, which might make it seem barren, But it is this very lack of substance that allows the subtle effects of dark energy to become visible, and it is this same void that may be pointing us toward a reality of multiple universes. Its emptiness is not a lack of information, it is itself a profound source of information. It teaches us that to understand the universe we must study not only the brilliant fireworks of stars and galaxies, but also the vast, quiet and seemingly empty spaces that lie between them. The most important answers may not be found in the light, but in the profound and patient darkness. One of the key puzzles is the formation of such a large void. According to our standard cosmological models, small density fluctuations in the very early universe were the seeds for all cosmic structure. Regions that were slightly denser than average attracted more matter through gravity, growing into the filaments and galaxy clusters we see today. Conversely, regions that were slightly less dense than average would have become voids, as matter was pulled away from them towards the denser regions. This process works well to explain the existence of voids in general, but the Eridanus Supervoid is an outlier. It is at the absolute extreme end of what is possible within this model. To create a void this large requires an initial seed fluctuation that was exceptionally large and negative. It's not impossible, but it is, once again, statistically very improbable. This is another reason why theories like cosmic textures or multiverse collisions are so appealing to some scientists. These exotic events provide a natural mechanism for creating a very large initial disturbance, blowing a bubble that standard gravitational evolution would struggle to produce on its own. The very existence of the void, independent of the cold spot, is a puzzle in itself, a clue that the early universe may have been a more dynamic and violent place than our simplest models suggest. Let's think about the journey of light itself, the messenger that brought us this story. For 13.8 billion years, photons from the Big Bang have been traveling across the cosmos. They have witnessed the formation of the first stars, the assembly of galaxies, the birth of our own solar system. Their journey is the history of the universe. For most of that journey, they traveled through regions of average density, but then about 3 billion years ago, a group of these photons heading in the direction of a small, insignificant blue planet entered the Eridanus Supervoid. For the next billion years, they traversed this immense emptiness. This leg of their journey was different. The familiar gravitational landscape of clusters and filaments faded away, replaced by a profound and sparse quiet. It was during this phase of their journey that they were taxed by dark energy, losing a fraction of their ancient energy. When they finally emerged on the other side and continued their journey towards us, they were forever changed. They carried with them a permanent scar, a memory of the great nothing. When our satellites capture these photons, we are not just measuring a temperature. We are reading a travel log, we are deciphering a postcard from the edge of the cosmic desert, a message that took 1 billion years to cross and carries a secret about the fundamental nature of our expanding universe. Could there be anything truly hiding inside the void? While it's unlikely to be alien megastructures or anything from science fiction, there could be other subtle clues waiting to be discovered. For example, the void might not be perfectly uniform in its emptiness. It could have a complex internal structure with subvoids and faint, wispy filaments of dark matter. Mapping this internal topology could provide more constraints on the theories of its formation. Furthermore, astronomers are searching for other, similar supervoids in the sky. If the Eridanus Supervoid is truly responsible for the cold spot through the ISW effect, then other large voids should also have corresponding, albeit perhaps weaker, cold spots. Finding such a correlation across multiple voids would be incredibly strong evidence for the standard explanation. So far, the results have been mixed. Some studies have found a weak correlation, while others have not. This search for void spot pairings is one of the most active areas of research in observational cosmology. The Eridanus Supervoid may be the largest and most famous, but it's by finding its siblings across the sky that we might finally unlock its secrets. The story of the void also highlights the incredible power of dark matter. While the void is defined by its lack of galaxies, which are made of normal, baryonic matter, it is the unseen scaffold of dark matter that truly governs its structure. Dark matter, which outweighs normal matter by about 5 to 1, is the primary source of gravity on cosmic scales. The Eridanus Supervoid is, fundamentally, a region with a significant deficit of dark matter. Normal matter, like the gas that forms stars and galaxies, simply follows the gravitational landscape laid out by the dark matter. So when we map the positions of galaxies to infer the void's shape, we are really just seeing the tip of the iceberg. We are tracing the visible light to map the invisible abyss of dark matter. This makes the void an excellent laboratory for studying the nature of dark matter itself. Does dark matter interact with itself in some unknown way? Does its behavior change in these extremely low-density environments? Any deviation from our expectations could provide a crucial clue about this mysterious substance that makes up more than 80% of the matter in our universe. The emptiness is a stage, and on it, the universe's most elusive component might just reveal a piece of its character. Let's reconsider the multiverse theory from a different angle. What if the cold spot is not a bruise from a collision, but a doorway? Some highly speculative quantum gravity theories, like eternal inflation, propose that new bubble universes could be spontaneously created from the quantum foam. In some models, these new universes could branch off from our own, connected by a kind of quantum tunnel or wormhole. It is theoretically possible that the unique energy conditions at the heart of a primordial event that created the cold spot could be linked to such a phenomenon. This is, of course, pushing the very limits of theoretical physics and is not a mainstream view. There is currently no evidence to support it. But it's a fascinating thought experiment. Could this region of space, defined by its emptiness, be a sign of a place where our reality is connected to another? Could the chill we detect be the faint leakage of energy across a membrane into a newborn universe? It's a poetic and beautiful idea. It transforms the void from a symbol of absence into a symbol of creation, a place where the emptiness of our universe might give birth to the fullness of another, a cosmic womb hidden in the dark. The direction of the cold spot on our sky is towards the southern constellation of Eridanus, the river. This is a purely coincidental alignment from our perspective on Earth. The void itself is incredibly far away, located at a distance of several billion light-years. The stars of Eridanus, by contrast, are in our own galactic backyard, mostly within a few hundred light-years. Yet this naming gives the void a place in our human story, connecting it to the myths and legends we have projected onto the sky for millennia. Eridanus, in Greek mythology, was a celestial river. In some tales, it was the river into which Phaethon, the son of the sun god Helios, fell after losing control of the sun chariot and scorching the earth. It's a story of ambition, cosmic forces beyond mortal control, and a fall into a great abyss. It's a fitting, if accidental, namesake for this cosmic enigma. We too are reaching for the reins of cosmic understanding, trying to steer our knowledge through a universe of immense power and mystery. And in the direction of the mythical river, we have found a real cosmic abyss, a challenge that tests the limits of our own ambition to comprehend the whole of reality. let us consider the future evolution of the Eridanus Supervoid. As the universe continues its accelerated expansion, driven by dark energy, the cosmic web will continue to stretch and thin out. The great voids between the filaments of galaxies will grow larger and more empty. The supervoids like Eridanus will become even more pronounced. In the far, far future, trillions of years from now, this expansion will have pushed all other galaxy clusters beyond our cosmic horizon. An observer living inside a galaxy within the Eridanus Supervoid would look out into a sky of almost complete and total blackness. They would be utterly isolated, with no visible evidence of any other galaxies or cosmic structures. They would live in a truly empty universe. Would such an observer ever be able to figure out the Big Bang? Would they ever be able to piece together the history of the cosmos? The Eridanus Supervoid is, in a way, a glimpse into the ultimate fate of our universe, a future of increasing isolation and cold. It is a preview of the long, quiet night that will eventually fall when the expansion has pulled everything apart. By studying it today, we are reading a page from the universe's final chapter. The cold spot is not the only large-scale anomaly in the cosmic microwave background. While it is the most significant cold one, there are other features in the CMB map that are statistically unusual. For example, there appears to be a strange alignment of some of the largest patterns in the fluctuations with the plane of our own solar system, an alignment sometimes referred to as the axis of evil. This is another feature that our standard cosmological model struggles to explain and that cosmologists suspect might be a statistical fluke or an undiscovered systematic error in our data. The existence of multiple, seemingly unrelated anomalies could hint at a larger issue. It's possible that the cold spot is not an isolated problem but one piece of a larger puzzle. Perhaps there is a single, undiscovered physical principle or phenomenon that can explain all of these strange features at once. Finding that master key would represent a revolution in cosmology. For now, scientists are treating each anomaly as a separate case, but in the back of their minds is always the tantalizing possibility that these disparate clues, the cold spot, the axis of evil, and others, are all pointing to the same deep and undiscovered truth about our universe. The search for answers has led scientists to employ some clever observational techniques. One of these is studying the behavior of galaxies located behind the supervoid from our perspective. The light from these background galaxies has to travel through the void to reach us. While the integrated Sachs-Wolf effect is about the energy of light, the void can also act as a weak gravitational lens, or more accurately, a weak anti-lens. A massive cluster of galaxies would bend and magnify the light of objects behind it. A void, with its lack of mass, does the opposite. It should subtly demagnify or stretch the images of background galaxies. By meticulously observing the shapes of thousands of distant galaxies seen through the void, astronomers can look for this subtle statistical distortion. This provides another independent way to measure the depth and mass profile of the void. These gravitational lensing studies are incredibly difficult as the signal is very weak, but they offer a powerful cross-check on our other methods of mapping the void. It's another example of how scientists use every tool at their disposal, squeezing every last drop of information from the ancient light of the cosmos to solve this profound puzzle. Let's return to the most fundamental question: what is the cold spot? After all this exploration, we are left with a cosmic fork in the road. Path 1 is the conservative choice. It posits that the spot is caused by the supervoid combined with a random cold fluctuation. It's a coincidence of two known phenomena. It's statistically unlikely, but not impossible. This path preserves our standard model of cosmology. It keeps our understanding of the universe neat and tidy. Path 2 is the revolutionary choice. It suggests that the cold spot is a true anomaly, a genuine sign of new physics. It could be a remnant of a cosmic texture, a bruise from a multiverse collision, or something else entirely. This path leads us into uncharted territory. It would mean our best map of reality is incomplete and that there are fundamental forces and structures in the universe we have yet to even imagine. Science is currently standing at this fork. The evidence is not yet strong enough to definitively choose one path over the other. And so we wait. We wait for better telescopes, more data, and new ideas. The Eridanus Supervoid remains a silent sentinel, guarding a secret that could either solidify our place in the cosmos or open the door to a reality far stranger than our dreams. The existence of this vast emptiness can evoke a sense of cosmic loneliness. The idea that there are regions of the universe a billion light-years across that are almost entirely devoid of stars and galaxies can be unsettling. It emphasizes the vast distances and the profound silence of the cosmos. But there is another way to look at it. The structures of the universe, the filaments, the clusters, and the voids are all interconnected. They are all part of the same cosmic dance of gravity and expansion that began with the Big Bang. The void is not separate from the rest of the universe. It is an essential part of its pattern. The same laws that built our star-filled home also carved out the great nothing. There is a strange and profound beauty in this. It means that even in the most desolate and empty corner of the cosmos, we can still see the echoes of the same creation event that led to us. The void is not a sign of our loneliness, but a testament to our universal connection. It is the dark thread in the grand cosmic tapestry, and without it, the bright threads would not shine so brilliantly. Let's bring our journey to a close. We have traveled across a billion light-years of emptiness. We have peered back to the dawn of time, to the very first light of the universe. We have wrestled with the very limits of our understanding, contemplating the nature of dark energy, the fabric of space-time, and the possibility of other universes. The Eridanus Supervoid is more than just an astronomical object. It is a mirror. In its profound emptiness, we see the reflection of our own quest for knowledge. It is a symbol of the great, unanswered questions that still drive us to look up at the sky in wonder. It challenges our assumptions, pushes our imagination, and reminds us that the universe is under no obligation to make sense to us. The truth may be simple, or it may be fantastically strange. For now, the secret of the cold spot remains hidden, locked away in the silence. But the search continues. And the journey, as always, is as important as the destination. The act of asking the question is what defines us. And in the heart of the great nothing, the universe is asking us one of its greatest questions yet. Ultimately, the story of the Eridanus Supervoid is a lesson in perspective. On our human scale, we are surrounded by a world of substance, sound, and light. But on a cosmic scale, the universe is mostly empty space. The voids are the dominant feature of the cosmos by volume. We live on a tiny island of matter in a vast ocean of near-nothingness. This realization can be grounding. Our problems, our conflicts, our daily worries, they all shrink in the face of such immense, silent emptiness. It reminds us that our shared existence on this small blue planet is an incredibly rare and precious thing, a flicker of complexity in a universe that is largely cold, dark, and simple. The void is not a threat, it's a context. It is the vast, quiet backdrop against which the story of life, consciousness, and our search for meaning unfolds. And perhaps that is its ultimate secret. It isn't hiding anything inside its emptiness. Its emptiness is the message. It is the profound silence that allows us to hear the faint, beautiful music of our own existence. We have reached the edge of the abyss and peered into its depths. We are left with a profound mystery, a cosmic chill that could be a simple coincidence or a whisper from another reality. The Eridanus Supervoid remains one of the greatest puzzles in modern cosmology, a testament to the fact that even in an age of precision science, the universe still holds the capacity to surprise, to mystify, and to humble us. The truth is still out there, written in the faint, ancient light that has traveled so far to reach us. Thank you for joining us on this journey into the great nothing. The cosmos is full of such wonders waiting to be explored. And the biggest question remains for you to ponder. What do your instincts tell you? Are we looking at a simple, if giant, hole in the cosmic web? Or is this void the first real clue that we are part of something much, much larger? Share your thoughts in the comments below.